This is Kevin Lewitzky. This is my submission for Lab 5 for Intro to Logic Design. For this lab, we had to use the 4027 chip, which is the dual JK flip-flop, along with NAND gates to create a circuit that has one output, which is Z, which I have indicated with this LED right here, and two switches. One is X1 and one is X2. Those are these two switches here, and a pulse switch, which represents the clock, and that's this switch here. And for this circuit, if X1 or X2, one but not the other, are 1 and the other one is 0, then the output Z should not change state. If both inputs are at 0, 0, then Z toggles at every clock, and if both inputs are at 1, 1, then the output Z toggles at every other clock. So the way I have the circuit laid out is I've got the 4027 chip right in the middle. These two chips on the left are the quad 2-input NAND gates. That's the 7400 chip. And then these two on the right are the 333 input NAND gates. And those are the 7410 chips. And for this lab, I actually implemented it in Quartus prior to building it on the board because I wanted to make sure that I did everything correctly. And it definitely helped to do the next state tables on paper as part of the lab prior to using Quartus and then eventually building it on the board to implement it. What you had to do was put everything onto the K-map, so Q1 next state, Q2 next state, and then J1, K1, J2, and K2, and then use the K-maps to get the minimized sum of product equations to figure out how to make the connections. And then basically what I looked at is for J1 and J2 and K1 and K2, all of those involve an X1 prime, X2 prime, and then it's ORed with a combination of X1 ANDed with X2 ANDed with either Q1, Q1 prime, Q2, or Q2 prime. So the way I have it is it goes from the two switches here over to the 2-input NAND gates, and I basically use those as simple inverters to get X1 prime and X2 prime. And then I put those through a third NAND gate on the same chip to get X1 prime ANDed with X2 prime, and then the prime of that because it's a NAND gate as opposed to an AND gate. And then over here I've got on the 3-input NAND gates, I've got for each of those there's an input coming from X1 and X2 along with either Q1, Q1 prime, Q2, or Q2 prime. And then finally I put those through this chip over here through a NAND gate on this side in each one of those along with one of the outputs from this chip to get me my final equation. And then from there it goes to the output Z. Z is connected to Q1. And so the way it behaves is if both switches are up, Z will toggle on every other pulse of the clock. If both are down, Z will toggle at every pulse of the clock. And if these are in different positions, meaning 1 is up and 2 is 0, or 1 is 0, 2 is 1, then Z will hold its state. Okay, the first thing I'll demonstrate is with both inputs X1 and X2 in the low position. You'll see that the output Z toggles at every clock pulse. And the next thing I'll demonstrate is with only X1 in the high position. You'll see that Z does not change state. You'll see that every time I pulse the clock, Z does not change state. I'll switch those. I'll put the second switch, X2, into the high position, move the X1 back into the low position, and you'll see the same thing happens. Again, every time I pulse the clock, there's no change to the output. Now I'll put both switches back into the low position. I'll pulse the clock once. That way the output is on. I'll put X1 back into the high position just to show for this scenario as well, Z will stay high. And finally, I will put X2 into the high position, move X1 back into the low position, and pulse the clock. And again, Z does not change state. And for the final part of the lab, anytime X1 and X2 are both in the high position, then the output Z will toggle at every other clock pulse. So I'll move X1 into the high position. So now X1 and X2 are both high. And every other time I toggle the clock, I pulse the clock, then Z will toggle.